Welcome back, everybody. I want to spend just a few minutes going over a couple of questions on the worksheet that people seem to have difficulties with. And then we'll get into a little bit of new things and then give you some time to actually work on your homework. So questions 5 and 6 on your worksheet from last time caused people a little bit of problems. So I just want to quickly talk about it. You're creating velocity graphs from the position versus time graph. How do you figure out velocity? Well, remember, velocity is the change in the position, delta x, over the change in time, delta t. So in this case, if you look at this original graph, the slope of this, which is actually what delta x, delta t is, it's kind of constant. In the first 1 second, it went 1 meter from 0 to 1 meter, and it did that in 1 second. So what was its velocity during this first part here? It was 1 meter per second. And so we actually represent that here. Well, you can do the same thing also for the next couple of seconds. And some of you are like, oh, wait, this first comma's too easy. Yeah, here's another, it goes another 1 meter in the next 1 second. In fact, all of these are exactly the same. So all the way out to 4 seconds, it goes 1 meter each second. So our velocity here is just 1 meter per second all the way out to 4. And that should be a nice straight line. Let's take a look at this next one. A little bit more exciting. I'm going to do the first second again. And let me draw this out, both these out first. The first time here, it goes 2 meters in 1 second. So our velocity during this time is 2 meters per second. So if you draw it on the graph over here real quick, it should be 2 meters per second for the first second. Then our slope over here, and you could do the whole thing. It's all one of these. And if you look at it, during this time here, between 2 and 5 seconds, I go up 2 meters in a total time of 1, 2, 3, in 4 seconds. Distance over time, 2 meters over 4 seconds, means my velocity here is actually going to be 0.5 meters per second, which should bring us right in here, if I can draw a straight line there. And you don't have to label it, but just sort of you can visualize it. This is 0.5 and this is 2. If you want to, you can put a little dotted line between these two, but that is optional. Oh, and then this one here. I don't remember which number this one is, but let's take a look at this one because it has a negative part. During the first 2 seconds, in this 2 seconds here, we go up a total of 2 to 4, 2 meters, which means during this time interval, our velocity is 1 meter per second. So between 0 and 2, I'm at 1. So straight across here, kind of draw it that way. And now this next part. We actually go down a total of, I'm going to draw all the way down here. We go from 4 down to 0, which means we actually go down 4 meters in 2 seconds. Our velocity, which is the change in position over the change in time, is now -2. So during this next interval between 2 and 4 seconds, we need our velocity to be -2 meters per second, which is all the way down here. Again, this is between 2 and 4 seconds. We don't know what's happening next. If you want to, you can do a little dotted line that connects these two just to make it look a little prettier. But again, the dotted line is optional. Good. I hope it feels pretty good about doing that. Here's our new things here. The question is, what does the purple shaded area of a velocity versus time graph represent? In other words, I'm asking you, what's the area underneath a velocity versus time? In the previous worksheet, we were going from position versus time graphs to velocity versus time. Here, I'm actually giving you a velocity versus time. And I want you to think about this for a brief moment. What would happen if you went 30 meters per second for 6 seconds? Well, if you're going 30 meters per second, that means you're traveling 30 meters every 1 second. If you keep doing that for 6 seconds, you'll actually travel 180 meters. Well, it turns out That's exactly what this is. It actually tells you the displacement, delta x. And if you work it out real quick, there's something interesting. This is strange. In math class, height was always just a pure number. Width was always a pure number. But in this case, the height is 30 meters per second. The width is 6 seconds. And something happens if you multiply those two. The seconds here cancel the seconds in the denominator here, and so you end up with just meters. And so the area of this thing, which is your displacement, your change in position, is equal to 180 meters. What does that tell you? It tells you how far you traveled during this time. You're like, oh, Mr. Clemmer, that means our position's 180 meters? No, it means our change is that. It could be that we start out at 0 meters, and at the end of this, we end up with 180 meters. But it could also be that what happens if you start out at, say, 20 meters, and then you go 30 meters per second for 6 seconds, your displacement would be 180, which means you'd actually end up at 200 meters. So this area tells you how far you travel, not absolutely what your position is at the end of that. Let's try another one. What about this one? Well, the displacement is going to be that purple shaded area. Do you remember how to find an area of a triangle? It should be 1/2 base times height. So in this case, if we do that, again, seconds cancel, and we end up with just pure meters. 1/2 times 40 times 4 is 80 meters. And so that's our displacement during this time, how far we travel while we're doing this one. And so it's pretty straightforward. You're like, okay, I got it. But it gets a little bit more exciting. In this case, we've got a trapezoid. How do you find this one? Well, if you don't remember the equation for a trapezoid from math, which here it is down here, I'll give you a quick trick. You can actually break it into a rectangle and a triangle. And then you could find the area of this rectangle and then add it to the area of this triangle. But let's go ahead and use this formula since I gave it to you. Just plugging in our numbers, our base is 3 seconds wide, from 2 to 5 seconds. That's 3 seconds wide. First height is 20 meters right here. Second height is 50 meters here. Plugging in those for these two numbers. Turns out again, seconds will cancel, and we get our displacement is 105. And now here's where it gets a little exciting. Don't worry too much. We can write this. We know the area is equal to the displacement, delta x. So 1/2. The base is just the change in time. In this case, 5 minus 2, which would have been 3 seconds, but in general, just delta t. Our first height is the original velocity, v sub o. And our final height is the final height of this thing right here, which is v final. And so we've got this, and so we can come up with a general equation. I don't want you to be able to do this, but I just want to show you. If you rearrange that equation, you get this one. And notice it's surrounded by a red box. Why? Because it's actually one of my favorite equations. And you might say, whoa, wait a second. I don't get it. V original plus V final divided by 2, what is that quantity? Well, it turns out, think about it, this is what you do if you're averaging two numbers. What is this quantity inside of the brackets here? It's actually our average velocity. I'll call it V sub av. And so in that way, it makes a lot of sense. What's your displacement? Well, it's your average velocity times time, if that makes sense. Just like before when we had the rectangle going 30 meters per second for 6 seconds, displacement was just your velocity times time. Here it's your average velocity times time. This equation is one of the big ones. We'll use it a lot in the upcoming days. Take a quick look at it. I want to show you a quick application of it. Here's a plane being launched off an aircraft carrier. It goes from 0 to 76 meters per second in 2.5 seconds. I timed the video. And my question is, what's the length of the catapult? It's literally, I call it a plug and chug problem. You plug the numbers into the equations, chug it through on your calculator, and you get an answer. In this case, just so showing you, start the initial velocity, original velocity is 0, final velocity is 76 meters per second, and the time is 2.5 seconds. And if you solve this, you'll discover, oh, the catapult on the aircraft carrier is about 95 meters long, or about the size of our football field. It takes a bit to get it all the way up there, which should make sense. I want to introduce this next concept because you just saw it for that plane. The plane went from 0 up to 76 meters per second in that 2.5 seconds. We can actually talk about the plane's acceleration. Acceleration is how much your velocity changes in some amount of time. So the acceleration of that plane in the previous problem would have been it gained 76 meters per second in a half a second. In general, though, we can sort of leave it this way. It would be the final velocity, which in our plane was 76. The original velocity was 0, and our time was 2.5 seconds. And I got to grab out a calculator real quick to solve this one. What's 76 divided by 2.5? Yeah, okay. Its acceleration actually gives you something like 30.4. And you might say, well, what are the units for this? Well, the units are an interesting thing. Velocity is measured in meters per second. I could put it on the 0 as well. And time is measured in seconds. So our units here are meters per second divided by seconds. Mathematically, that's actually equal to 30.4, and please forgive me if your algebra is a little rusty, meters over seconds squared. In some ways, I actually like this one more. This one tells me my plane is gaining 30.4 meters per second every second, which in some ways is a little bit more easy to understand. But now let me take this a little bit further. I think it's on this slide. Yeah. You can actually rearrange it and do this by multiplying both sides by t. So if I take this t and move it to the other side, you can get that. Or rearranging it, you can get this. If I add v0 to both sides, getting rid of on this side, move it over, you can get this equation. This is the other red box equation. This one allows you to find the final velocity if you know the original velocity and you know the acceleration of the object and the time that it's accelerating. It's kind of a fun equation. We'll use it a lot. Let me show you a quick example problem of this one. The tallest building in downtown LA is the Wilshire Grand Center. If you drop a tiny ball from the top, it reaches the ground after falling for just 8.27 seconds. My question is, what was the acceleration of the ball? In this case, what's accelerating the ball? Well, it's actually gravity. So we're going to find the acceleration of gravity. This is a plug and chug problem, but the algebra is a little bit challenging. So my final velocity, negative that. You might say, wait a second, why is it negative? Well, just like we usually make towards the right positive and towards the left negative, when we're working vertically, we tend to make up positive and downward negative. And the ball's final velocity, it's heading downward, so it's going to have a negative for its final velocity. I kind of gave it away here when I wrote it down. The initial velocity of the ball is 0. The time it takes to hit the ground is 8.27 seconds. And so when we get this equation, we just have to solve it. At this point, you end up, if you divide both sides by 8.27, you'll discover our acceleration is negative 9.81 meters per second squared. Turns out that's the acceleration due to gravity in downtown LA. And it's pretty much the same everywhere on the surface of the Earth. Anywhere you go is about this. Any dropped object will gain 9.8 meters per second every second it's falling if it's near the Earth's surface. So we've got these two equations, and I'm going to do something really quick here. I don't want you to stress out about it. We're going to take the two equations we've been using and combine them together algebraically to get a third useful equation. The issue is this. We've got final velocity here, we've got final velocity here. What am I about to do? I can substitute this in for the final velocity over here. And you're like, oh my goodness, what just happened? It looks ugly. We've substituted this in for v final. And it looks ugly for a moment. Just go with me for a moment. Gives me that all over 2. And if I divide both this piece here by 2 and divide this one by 2, separating it out, you'll end up with this expression. If I multiply through by t, we get this. And this is our final third useful equation now. So the three equations in the three boxes here are ones where we've got velocity changing, where we're undergoing acceleration, and they're all very, very useful. In fact, I'll give these to you on the next test so you can actually use them. Well, they're actually going to be used in your home or your worksheet for tonight. Let me show you. Worksheet for tonight, first of all, you're going to be creating a velocity versus time graph, and then from there, you're going to do your calculations. So take a look at this one. First of all, we're going to graph this first one. A poorly tuned car can accelerate from rest to a speed of 28 meters per second in 20 seconds. Rest means it starts out at 0. And since we're making a velocity versus time graph, after 20 seconds, it's going to be going 28 meters per second. So I'm just going to create some arbitrary marks on here. Try to draw as straight as I can. So after 20 seconds, it's going to be going 28 meters per second. Some of you might say, wait a second, Ms. Calmer, you're forgetting to put units. Well, the axes already have our units of seconds and meters per second. Our graph is going to look like this. Do you have to put the dotted lines on? No. I just did it so I could sort of draw this. A, what's the average acceleration of the car? To do that, you could either use, actually, let's go use this equation because it's one you're familiar with. And you might say, whoa, how do I know which equation to use? Well, in this case, we knew the final velocity. We knew the initial velocity. We're looking for the acceleration, but we also did know the time of 20 seconds. So solving this one, 28 equals 0 plus the acceleration, which we don't know, times the time, which is 20. I'm going to write it out just a little bit further so you can sort of see it. So 28 equals 20 times a. To solve for a, we're going to divide both sides by 20. And if you do that, you'll discover the acceleration is 1.4 meters per second squared. And I'd like you to put a little box around it. I forgot to put my square down there. Hold on, let me fix that. B, what distance does it travel? Well, for this one, we're looking for displacement delta x. We know acceleration when you use time. There's always multiple ways of doing this. One way of doing this is, if you remember, displacement's actually the area underneath a graph. You could simply find the area of this triangle. Alternately, you can do it mathematically, either with this equation. Your change in position displacement is equal to the average velocity, v initial plus v final. Sorry, trying to write small, all over 2. This is our first equation, all times time. Or you could use the last equation we just derived, where delta x is equal to v0 times time plus 1/2 at squared. Which one of these is the right way of doing this one? The answer is any way, any three of these would actually give you the right answer. I think the area is actually the easiest way of solving it, since you already have the graph. But you should be able to sort of figure it out. Any of these, if you plug in and solve the numbers, you should discover, and I'm going to do 1/2 base times height, 1/2 times base, 10 times 28. Delta x is simply 280 meters. In other words, this object or our car is going to travel this far in that amount of time. That's not a very far distance actually going at the speed we're going. Let's take a look at a couple of these real quick. At t equals 0, a car has a speed of 30 meters per second. I'm going to go back to drawing this. So 30, and I'm just going to put that right up here. And then a little bit later, it's going 14. That's just a little bit under half of that. So it starts out there, and after 6 seconds, I'm just going to put my 6 over here, it's going to end up there. I'm just kind of drawing a few things here so I can kind of get myself in the right spot. So it's going to end up here. It starts out here. And so my velocity versus time graph is going to look like this. In this case, the only thing we're solving is the average acceleration. And just sort of so you can sort of see it, I'm probably going to go ahead and use this equation again to find acceleration. V final equals V initial plus acceleration times time. And sorry, it's actually taking me so long to write this. Oh, my A didn't show up very well. Sorry. There we go. Final velocity is 14. Initial velocity was 30, our original velocity. And we don't know the acceleration. We're going to leave that as a variable. And our time is 6 seconds. Solving this one, I'm going to subtract 30 from both sides, which gives me negative 16 is equal to 6a. How do we solve for a? I'm going to divide both sides by 6. And grabbing my calculator, 16 over 6 is, 16 divided by 6 is about 2.67 meters per second squared. Again, remember the units for acceleration, meters over second squared. At this point, you might feel pretty confident. I was just going to do 2 more examples with you and then let you work your way through this. I think the page only has a total of 5 questions. I'll let you do 3 and 4 on your own. Well, wait, let's see. Let's do number 4 together. I'll have you do number 3 and 5. A bus is initially moving at 20 meters per second. It slows at a rate of 4 meters per second. So it starts out here at 20. How long is it going to take it to stop? Stop means its velocity goes to 0. And some of you can think about this logically. It's losing 4 meters per second each second. What is that? That's its acceleration. It's losing 4 meters per second each second. Its acceleration is negative 4 meters per second squared. Logically, if you lose 4 every second, some of you can very quickly figure out, oh, it's going to be 5 seconds logically. But you might say, wait a second, how am I going to solve that if I don't know, if I can't do it logically? You can use this. V final equals V initial plus A times T. And this is the reason I'm doing this one with you. Final velocity is 0. Initial is 20. Forgive my drawing. And here's the only one you've got to be careful on. You have to realize it's slowing at a rate of 4 meters per second each second. That means its acceleration, it's losing 4 meters per second every second. Its acceleration is negative 4 meters per second squared. And that times time. And if you can solve it real quick, we end up with this. Negative 20, and I'll leave off the units here just for clarity, equals negative 4t. And then if we divide both sides by negative 4, you'll discover that, oh yeah, the time is 5 seconds. And you've got it. Last question. How far does it travel while it's braking? Well, one way of doing it, and again, I think it's one of the simplest ways, is to find the area underneath the velocity versus time graph. What's the other option? Well, we can use either one of the formulas for delta x. Again, I don't know if I need to write it. Delta x is equal to initial velocity minus final velocity over 2 times time. Oh my goodness, that's a really bad v. Or you can do the other one, which is the long one. I don't think I can even fit it at this point. I've gone too far, where delta x is equal to v0t plus 1/2 at squared. Or just find the area. I'm going to do the area. So 20 is the height, 5 seconds is the width. I shouldn't have written 5 over here. Let me remove that because it's already got the unit here. What's the area of that? Well, you can do 20 times 5 is 100 times 1/2. Delta x is going to be 50 meters. You would also get that same answer if you used either one of the two equations for delta x. Again, which is the right way of solving this? Any which way you'd like. In your worksheet tonight, you can work with a neighbor or you can try it on your own. It should be not so bad. We'll come back and practice some more of these problems later.